That's right. I will continue talking about language servers and DSLs. And in particular, I want to tell you about how you can make it easier on yourself to develop a language server for your DSL. So we're going to jump right into it. To the right here, we have an imaginary DSL, which is intended to do one thing. It's a standalone DSL, and that thing is it should plot something. It is a very simple DSL. It has only like 3 different constructs. It has function definitions. It has constants or variable definitions. And then it has this plotting function, which we use to plot something in a specific range. And what makes this DSL a little bit different from other DSL that you might have seen is that this DSL supports higher order functions. So you see this parameter, this h, the first parameter to the function f, is later used as a function. So that's what makes it a little bit different to other common plotting functions. But it is an imaginary example. And well, as we've already seen in the previous talk, it is a standalone DSL. It does one thing well, plotting, hopefully. And it has a custom syntax, and consequentially, it also has like a custom parse and validation. And the moment we have a custom parse and validation, we have an issue. We have no outside-of-the-box tooling for working with a language like this. So in fact, when we open this example in our editor, it doesn't look like this. It actually looks like this. So we have nothing. We have no syntax highlighting. We don't see errors when we do something wrong, and that's in general very hard to work with, right? So it is much better if we have at least syntax highlighting, and even better, we would like to have some basic toolings such as documentation on hover or go to definition and so on and so on. And the easiest way, or at least I claim the easiest way to get some basic tooling support is to implement a language server. But that posed the question, what kind of features are we actually expecting from our language server? And how can we prepare our DSL when developing it so to make it as easy as possible to implement the language server? To illustrate that, I'm going to show you very briefly a different DSL, which has all these features that I want to talk about in particular. This DSL has been developed by co-workers of mine and me. And it is intended to be used for legal drafting and to help legal drafters to draft laws. As such, it is a very small functional programming language and with some other features on top, but we're not so much interested in that. We're mostly interested in the IDE features that we have here. So the basic thing is, or the first thing that I would realize here is we have syntax highlighting, which is already pretty good. Other things that we have is like we have basic code navigation support, or like code navigation support that we want. Sorry, I should maybe explain a little bit what this syntax does. We have here like this is a normal parameter. Here we're specifying what is the return parameter, and here's the function definition. So this is the body of the function called factorial. So it's not important, but so that it's a little bit easier to follow. And when we hover, for example, over our n, we get the information that this is a number. So we have some help in the code navigation. Even better, when we're asking to where does the definition go, or like where is this token defined, it sends us right up to this n, which is where it is defined. So that's what and when we write something, so for example, we are starting to write another function, and then we have an error message here. The parser says, okay, this is unexpected because it's a layout-based language. It thinks here it continues. Either way, when we start, the issue now that another issue that we often have is when we are working with an IDE, then I just keep sitting. When we're working with an IDE, the issue is that we often are mid-sentence because we are thinking about something. I started writing a function, but now I'm thinking, what are the actual parameters? And maybe now I'm starting to browse code. So an IDE should still keep functioning even when our program is in an inconsistent state. It's like this. So even though this program does currently not parse, so consequently it does also not type check, we still would like to have some basic code navigation features. So for example, when I hover over this n, I still get the information that this is a number. And if when I'm asking where is this defined, I still get this kind of information. And this even works in this case when the function itself is broken one way or another. For example, when I'm removing the else, and I get here another parse error, I can still ask for the information, what type is this n? And the go to definition still kept working. And that is something that at least I believe is a very crucial part of an IDE, that it keeps working even when the code is broken. So we're going to talk about, excuse me, I'm removing the cursor. I want to talk about what you can do as a DSL author to make this kind of IDE interaction easier on yourself, so that it's quite easy to implement and also quite a lot of fun to implement such a language server. For this talk, we're going to talk about syntax highlighting in particular. First, because it's very nice to get syntax highlighting via the language server. And second, because it turns out if you can do proper syntax highlighting via the language server, all these other features, such as code navigation, code refactorings, and displaying diagnostics like this in the editor, are actually much easier to implement, because the syntax highlighting lays great foundations for all these other features. So, what do we actually want from syntax highlighting? Is this, okay, this is a little bit small, I'm sorry. I'll try to explain it. What do we actually expect from syntax highlighting that we have in the editor? Well, very basically, we have keywords. So for example, this plot, or symbols like equality sign and comparison operators. We have literals, and like 0, 1, and 2, and also 5, and so on, that we want to display differently than operators and keywords. And then we also have comments. This is unfortunately due to the, I think, very difficult to see, but here is a comment, which is like, is using Haskell infix inline comment syntax, where we are writing the very helpful comment that this Z is a multiplier. Documentation is awesome. And we also want to highlight things that are like a little bit more dynamic. So for example, names like Z and X are constants or variables or parameters. So we want to highlight them. We want to highlight them differently than functions. So that makes it a little bit easier on the eye. So like to figure out, for example, whether a variable is a function or a variable. And something that we get from syntax highlighting via the language server that we don't get that we don't easily get, or if at all, from grammar-based syntax highlighting, is that this H here in the third line is actually highlighted blue because it is a function. And this is why I'm actually advocating for saying syntax highlighting via the language server, because it gives us additional semantics that we couldn't use otherwise. Okay, so that means to provide this kind of syntax highlighting, we first need to take this program and pass it into our AST. This is an example AST. It's in Haskell. I hope it is easy enough to follow. There's nothing really complicated going on. We're defining a couple of types, the necessary types that we need to actually pass our program into it. For example, this definition is supposed to be, for example, everything that's an assignment, like this one, the first line, the functional assignment, and the constant assignment. Then we have a name, which is the left-hand side of our equality, and then we have a general purpose expression where we have all the basic constructs that we have, like function invocation, basic arithmetic, and not so basic arithmetic, whatever you want. So if we pass this program into our AST, then we try to provide syntax highlighting based on this AST, we're going to run into some problems. Namely, this AST does not really store all the information that we need to actually provide accurate syntax highlighting. So for example, in line 3, we do not actually capture in our AST that there's a new line now and that the body of the expression is on the next line. Similarly, we have a comment here. This comment is nowhere represented in our AST, which makes total sense because comments are part of the concrete syntax tree and not part of the abstract syntax tree. So it is usually, you would say, you would be crazy if you had a comment in here somewhere. Okay, but how do we continue from here? What do we do to fix that? What we want, ideally, is we want to store all the source locations of the tokens that we have actually in our program, like on the left side. We want to know this is in the first line and the first character. And we also want to store them in our AST as uniformly as possible. We do not want to sprinkle all that kind of source locations all over our AST, because that makes it much harder to work with our AST and makes it not like it turns our AST into something that is like not really abstract. It's really much more like reflects the actual grammar of your program, which is like not abstract. Let's put it like that. So our solution to the problem is introducing the annotype. The annotype, which is an abbreviation for source annotation, is basically our kitchen sink to put everything that we need to provide all kinds of IDE features, or like especially syntax highlighting, and without trying to like put a lot of types into our abstract syntax tree, so to keep it as abstract as possible. Again, this annotype will store all the past tokens of this program as originally as originality, so that we can accurately reproduce them. And we also have to add one annotype, or like one type of this, or like one value of this type, to each and every one of our constructors of our AST, since our AST usually corresponds to one or more concrete syntax trees, right? Okay, but what do we actually store in this annotype? It won't be like we are not storing the all tokens in the definition here, because that would be quite redundant, and because the name would also want to store like this information, for example. Okay, so we're going to take a look at the concrete example of line 3 of the previous program, and we try to figure out how we are constructing these source annotations. The first thing that we're noticing is that there are many tokens that are not actually really part of our definition, or like of this definition type where we only kept the name and the expression. For example, everything left of this equality sign actually are tokens that are part of the name node. So we do not really want to store that kind of information in our definition. Similarly, everything right of our equality sign should be stored in the expression node, and not in the definition. Okay, so how do we represent this? We represent it like this. I'm afraid this is a little bit low. I hope people can see this from here, but yeah. Anyway, so instead of storing the concrete tokens that we've passed, we rather store placeholder. And this placeholder value points to the first child, or like it is the second child in the AST, but I'm going to say it's the first child of the abstract syntax tree node of definition. And then we're storing the concrete token that is actually part of our definition, in this case the equality sign. Then we have another placeholder, which is for the expression node, which is the second child of our definition. And then we say, and then at last we have a semicolon, which is part of our definition, or like which is a concrete token that is part of the definition. And this process we can just repeat until we have reached no placeholders. So this full line now, let's follow it through at least for the beginning. When we have this placeholder points to the source annotation of our name constructor, which in this case is this one, the function name constructor, because this is a function on the left-hand side. And what we have here is we repeat the process that we had before. Some tokens, like the name, we don't want to store, like not part of the function application, not part of the name. They're actually part of the variable that we have here. So instead of saying we're storing an f here, we're storing a placeholder here, which will then in turn point to the variable which contains the actual past tokens. We repeat this process. We have here we store the open parentheses because we say that is actually part of our function definition, the name definition. And then all the parameters are also stored as placeholders. When we go up here again, we follow the next placeholder for the expression. The expression naturally has two placeholders again. One for the left-hand side of the multiplication operator and one for the right-hand side of the multiplication. And the left-hand side we need to recurse further into, but that's too much for these slides. But the interesting part is now how we actually store comments, because we need to attach this comment to our concrete token Z in order to remember it. We want to remember this comment. So what we do is we still store the concrete token, that we are still storing the token, the past token, but we're marking it as a comment so that it is not part of the abstract syntax tree and not part of the source span later on for this Z, because this annotype, since it stores all the past tokens, can also be used for storing all kinds of source locations, even for the full node, for example. Okay, that's how we represent them, and that's quite convenient. So that allows us now to pass this program into our AST without losing any kind of information. that is quite useful in general. Is that a question?
Yeah. What about the white spaces? I noticed that in your representation there you had a space before the comment, but it wasn't there in your annual.
Yes. I was hiding that. You're completely right. What we do now, I would not be coming back to it. So let me say we are storing all kind of trailing white space with the parsed tokens. So in this case, there was a new line after this equality sign. So in this representation, we would actually store this new line as part of our equality sign. So technically speaking, we don't really need to provide the features that we want, but it is actually quite convenient to store all kinds of white space, because then you can do like exact printing, like parsing a program and printing it out exactly like it was, which can be convenient, but it's not a necessity. What you only really need is the location, like this is on line 3, but this is on line 4. Okay, so why is the anotype good? Well, it's a single source of truth, so we do not pollute our AST with all kinds of information that is part of the concrete syntax tree, and it turns out that it is sufficient for implementing most IDE features. I'm saying most because I've not implemented all. So for all IDE features that I've implemented, this anotype was actually very much helpful for implementing these features. There's though an inherent trade-off of this anotype representation. It is very flexible, so you do not really impose an order on the parsed tokens of your grammar, but there is the issue is that you have less type safety, because like there's no reason that there's no guarantee that the placeholders that I need here are actually in the source annotations. We think this is an acceptable trade-off, but it is a trade-off nonetheless, and it can usually be you can usually avoid this type safety issue by construction when building actually the parser. Okay, so what do we do now? Now we have passed this source. Now we've passed this program. How do we actually now derive syntax highlighting from our AST? So we're taking a look at our source annotation again. And what information, first we need to know what kind of information do we actually need to generate, right? Because like what? So in the language server protocol, what we're generating is this JSON payload. I'm sorry for the size. What it contains information, just as a high level, it contains the information where does a token start, at which line and which character, how long is the token, and what is the semantic value, like what is the intended semantic of that token. So in this case, if we were to color the third line, we would like to say the first token, which has the length 1, should be highlighted as a function. Then comes a symbol, the open parentheses, followed by another function. Right. How do we actually generate this JSON payload? Well, we simply have to traverse our source annotations. We start at the very top of the source annotation of our definition node, and then we just follow it from left to right. First, we realize, okay, there's a placeholder here, so I don't know what the first token is. So I recurse into the source annotations of the name node. In there, we realize, okay, the first token is still a function, is still a placeholder, so we have to recurse even further down into the name. So we essentially, this is like an AST traversal in its, essentially it's an AST traversal. There we realize, okay, the first token at line 3 and starts at character 1, because we store that kind of information in these tokens, is a function. We can use, since we are producing this syntax highlighting while we are traversing our AST, we can use contextual information that we have available in our tree. So for example, we know this token is a function because it is used, like it is in the function constructor. So once this is done, we recurse back up. Then we report, okay, here's an open parenthesis at this location, and then there's a placeholder here again where we find the age. And here we can use our type checking information or like type inference information to say that this age, since it's used as a function later, should also be highlighted as a function. And so you basically generate full syntax highlighting for a full program by simply traversing the AST by the source annotation of the tree. Yeah.
How do you know the line number? Because in your AST you have only like the semantics of the program, but here you have like a specific information on where is a token located.
Yeah. So we're not storing just strings here. what we store is we store tokens. And in these tokens, we have source locations. But it's a little bit harder to visualize. That's why it's a string here. The placeholder is also not a black dot. For that.
No. But I thought that in your anode type, you only store like the strings in the text.
Yeah, that's right.
But you have more metadata.
Yes, we actually have much more information available.
Okay.
Yeah.
But with this age, the AST, the syntax is not sufficient because you need type information, and I think you need complete scope information. What kind of age is it? And so
Exactly.
how does it relate to the sentence you said at the beginning? It should also work when the file is not in a consistent state.
We will come back to that. So I will say, sorry. Let's wait a couple minutes for that. Okay, because that's actually we're starting to cover it right now. So the issue is, no issue yet. Looks great, right? Now we have syntax highlighting based on our AST, mission accomplished, right? Now we start working on something, we add another line, something I stopped here and said I need to think about it. What happens next? What happens now? We try to pass the program fails to pass because it's incomplete, suddenly our syntax highlighting is gone, which is not great, right? That's not what we want. It's you would have horrendous flashy signs every time you write something. So that's not what we want. And it is kind of silly, right? Because we do have perfectly fine syntax highlighting available if we just ignore this part, right? Okay, so how can we do that? How can we reuse these old results? Okay, and what we actually want is something like this. We want syntax highlighting for stuff that hasn't changed, and we want to ignore the syntax highlighting for stuff that changed, right? And to do that, what we need is conceptually in the language server, we need access to the last time our program passed. So we need access to the AST, the last time it passed. And then we need a function, which is called, in the Haskell context at least, position mapping, which tells us exactly how the file has changed since the last time this value was obtained. And it doesn't require a lot of imagination to realize that we would like this kind of feature for many things. So similarly, for go to definition, if it would be completely fine if we say, okay, I want to if I want to go to definition while the file doesn't pass, we would like access to the last time the AST passed, and then we just check whether that part of the AST has changed. If it hasn't, then we can still reuse the old results. And the bigger the language server becomes, the more such things you can find. That you want some global state, and you want to remember and you want to remember how the document has changed since the last time you have executed it. And since every talk so far had a reference to a paper, here's my reference. And so a couple of smart people actually thought about IDEs a lot, and they realized that language servers and build systems have unexpectedly a lot in common, or like they have very similar requirements. So what are they proposing? So what they proposed is to implement a language server on, to implement a language server on top of a build system, and then they called it the Haskell language server, which is great news because the Haskell language server is still in use today and it's not abandoned, which means that what they are proposing in this paper does not only work in theory but also works in practice. So let's borrow from that idea. And the main idea is that we use a build graph to model expensive computations and track the dependencies that the different compiler phases have. So for example, we have here a so-called parse rule, which instead of being like a monolithic function that takes care of reading the file, then parsing the file, then reading the file, then lexing the file, and then parsing the file, for example, we have a rule that takes just care of, I assume that I get the lexed sources, and then I can just parse it, and then report it as a result. This parse rule depends on the read file contents rule, which just takes care of reading files. And then whenever we ask for this whenever we ask for the results of this rule, it just gives us that result instead of reparsing the same thing over and over again. And similarly, the parse rule, that's very, very helpful. It doesn't reparse whenever we ask for the result. It just computes it once, then checks whether the dependency is up to date, in particular whether the file has changed, and then if it has, then it recomputes, so it has dependency tracking, and otherwise gives us the latest result. And additionally, if this rule fails, we can still query it for the latest result, the last result it ever had. And in addition, which is also why it's important here, for each of these rules individually, we have this kind of position mapping available. So for each rule, we get a function that tells us what has changed since the last time, what has changed since this rule was executed compared to right now. Okay, so we can so in our rule, the solution is now we turn our syntax highlighting, our semantic token generation, into a rule, and this rule has access, and this rule then has access to this position mapping. Position mapping, in particular, does then the following: it remembers, like it knows what has changed, because a language server from the very design principles, a language server sends us just the changes, what has changed in your document, and it doesn't send us everything all the time. So it is actually very cheap and very easy to build this kind of position mapping. And in this case, here we have the old results. This is the old result of the semantic token highlighting. And then we can use this position mapping to say this line 3, like the semantic token that previously was on line 3 has now moved because to line 5 because we've just inserted 2 new lines. And we can do that with all the tokens that we have to get the result that we want. So now we are almost done. This is great. Now we have syntax highlighting for all the parts that have not changed, but there's one more issue that I want to tackle, and that is that this new code fragment has no syntax highlighting, and that's also actually no good. When was the last time you worked on something and you had no syntax highlighting until your program actually passed? That's besides that it would be much harder to write code. It would also be well, a little bit ugly, and you have all the colors keep flashing when stuff doesn't pass, right? So our solution to that is what I coined the term multi-phase syntax highlighting. I do not know whether other people already had a better name for this, but I name it multi-phase syntax highlighting. And the different phases that I'm referring to are the phases of the compiler pipeline. So we have a lexer phase usually, often, not necessarily, but we could have. We have a parser phase and we have a type checking phase. And we can provide syntax highlighting based on all of these different phases. So for example, at the very top right, we have syntax highlighting based only on the lexer results. In the lexer, we don't have information like whether that's a function or whether it's not. We only know this is an identifier, this is a symbol, this is a literal, and if we're very gracious, this is like an operator and stuff like that, and often enough comments, for example. And providing syntax highlighting based on the lexer result is simple because this program, while it is not a correct DSL program of us, it is still something that is correct, that we can lex correctly. It will fail to pass, but we can lex it. And based on these results, we can provide some kind of syntax highlighting. On the other hand, if we have information based on the type checking and parser result, we can generate syntax highlighting like this, where this incomplete is, we don't know what it is yet, so it doesn't have any syntax highlighting. And what we would like to do is, we would like to merge these kinds of things. And then have this result at the very top, at the very bottom, where we have the syntax highlighting of the later phase. So this function is highlighted as a function, but we have still some syntax highlighting for the stuff that we haven't finished writing yet. And this would be a good solution. Like this looks nicely, at least to my eyes. I mean, you can disagree with me in theory. But how do we express something that looks kind of complicated, right? Well, if we have a build graph, it turns out we can express this quite efficiently. Efficiently and also quite beautifully, right? So this may look intimidating, but it is quite straightforward. We have the normal parser pipeline where we say the lexer needs to write the file, needs to read the file, of course. Then the parser needs the results of the lexer. The type checker needs the result of the parse tree. And in each of these phases, we generate semantic tokens based on the result, based on these intermediate results. Yes, and then it is a very simple process. For each of these semantic tokens, we do the position mapping that we've seen to make sure that they are at the correct locations. And then we simply merge all the semantic tokens. Okay. I was way too fast. Well, so then we simply merge all the tokens, but we want to prefer the tokens from the later phases. In this case, we want the type checking syntax highlighting rather than the syntax highlighting of the parser. And we also want to prefer tokens from the parser step over the Lexer semantic tokens. Which brings me to the end of this presentation. Actually, surprisingly, because didn't think I would be that fast. What I wanted to say, or like what I want to also for you to take home, I think LSP is a very good fit for providing a modern IDE, even though as the previous talk actually has like highlighted that there are things that are not good with the language server protocol and makes it quite difficult to work with when you're not TypeScript or C#. Like in this case, when you're Haskell, or no, not in this case, but when you're Haskell. And a language server fundamentally requires different things from your AST than an interpreter, for example, does, because we need access to the original tokens. We need source ranges, we need the comments actually, even still stored somehow in our AST. And we need source ranges to provide accurate error messages, for example, which are actually like quite useful when type checking as well, since you want to highlight exactly where stuff is going wrong. What we've seen in this talk, we've seen a couple of tools that should help you, or like can help you implementing an IDE for your DSL. The first thing is this annotation type, source annotation type. What you need is some kind of source annotation type, which stores all the parsed tokens, and that make up the AST node in particular. Each source annotation stores placeholders, which are references to the source annotations of its respective children, which is how we are, and that is very easy to reconstruct because we simply have to traverse the source annotations to get the original sources out of it again. Also, build graphs, or like an incredible, helpful, and powerful tool to implement IDEs, because it turns out having access to outdated information and this kind of position mapping makes it incredibly easy to provide basic IDE features that we would like to have in our everyday life. What I've shown you at the very beginning, this L4 language, is hosted in here. There's a lot more going on there. If you're interested and want to take a look at it, there's a lot more going on in there than just syntax highlighting. So it might be a little bit hard to find what you're interested in. I created another DSL example based on BNF rules, or like not based where you pass BNF rules. That should be much easier to digest if you're interested and if you want to read a little bit more about this system. That was it. Thank you for your attention.
Yeah, really interested in how you did this anode data type, how you do the references to the child nodes, obviously the pointers. Can you show us the anode data type or explain a little bit about how that works?
Yes. So conceptually speaking, if you're interested, I can show you the code, but I think that might be a little bit much. Let's take a look at this. Yeah, this is good. So this hole, this is like the main thing is that we can traverse this annotation in order, and when we traverse it, we simply know that we implicitly assume that like we're essentially writing a traversal, and whenever we encounter this placeholder, we're trying to get the annotations from the child elements. So that is something that you can write by hand. This kind of like, whenever you encounter this placeholder, please use this child element. Or you can use generics, which is a little bit more convenient. And yeah.
So there's an implicit mapping of the first hole being the first argument after the anode type.
Exactly. Yes. It's not really a requirement. It just makes it easier and easier to explain. But you could switch it up, but then you have to switch it up in your traversal.
Okay, but that requires that my string order in which they come as a string has to be in the same order as which they come in my data type definition in the AST. So make definition, I can't put expression before name then.
No, you could.
I could.
You could. It just requires you that when you're writing the traversal, or like when you're deriving it or something, that you need to do that. You just need to like make sure that you switch it, because we need to traverse it in the order of the concrete syntax tree. Yeah. Yeah?
Question. How would you do this kind of IntelliSense or syntax highlighting in a way that you would want to do a quick fix? Like, would you write to, instead of this, would you write something else? So, because here I think that then you can actually parse this annotype because it's already having the references to everything. So, for example, if you want to say that instead of calling some here the multiplier, maybe you want to call something else here. So where would you plug in that in this process?
Well, what you can do is you do not actually need this kind of. That's where language server protocol actually is really, again, very useful, because you don't, like there are multiple approaches to do that. The first thing is you don't actually need to change your AST to like provide this kind of syntax change. Because what the language server only sees is text edits. So you need to compute the final text edit, then send it over, for example, and then you can parse it again, and then it is fixed. But it is generally what you can. It is these kinds of code actions to implement natively in the AST is a little bit complicated. That is right, but each representation of the concrete syntax tree is kind of like favors certain actions that you can perform with them, right? So it is very easy to do inlining with this representation, because you just take the tokens and just inline them, right? But it is very difficult to do some other things which I actually haven't tested out whether they are. Yeah, but your particular issue, where you say you want to replace the multiplication with, for example, an addition, you can implement probably in multiple ways. So first you can just say, okay, I'm looking for the concrete tokens that are in here, and then replace them, right?
Yeah, but let's say that you would have like 3 different multiplications, and you would like to combine it and say that, okay, would you like to use one instead? So kind of do this kind of code hints that maybe you want to do something else instead of typical. But the problem is that then you have already fixed here the annotype and the expression basically. So modifying both is kind of
well, in a way you can create new you can create new tokens, right? So you could just create an AST representation where you insert the tokens yourself without any kinds of source locations in that case, of course. But then you simply need to make sure when you're printing it that your program can handle that in a way. So this is not like a full framework that does all of that for you. If you need that kind of refactorings, you still have to need to implement them yourself, right? Does it make sense?
A framework was a good word for my question. So how flexible is that? So could I just take your implementation and plug my lexer, my parser, my type checker, and my AST representation, and then it should work?
Well, more or less. So it is more intended to be a library. It's not something that you say, so you can take the kind of things that you're interested in, and well, sorry, let me rephrase that. It is not a framework, but it's intended to be as a library. So it depends on what you actually need. You can take it, or you don't need to take it. So for example, the build graph is independent of this annotation type. But we are working on a framework, or at least I'm in this example, I'm trying to come up with a framework. Okay, that's true. Here I'm trying to come up with a framework where you do exactly that. So you simply define your data types, your syntax, you derive a number of type classes, and then you use, then you construct, then you parse it, and then you get a lot of things for free. For example, this language server you get for free.
All the infrastructure for the language
exactly.
server, communication and stuff.
Exactly. No, that of course. So like that's I'm talking
that's
about
a big relief already.
Yeah, I'm talking about features on top of that. So like this syntax highlighting, I actually removed that slide because I thought it didn't add anything. Apparently I should have added it. where you can say you have a utility function which just says where you just provide how you generate these semantic tokens based on your different compiler phases, and then it already does all of this. So you only provide this, this, and this rule, and the rest is done for you. So then you can then you get this very nice syntax slide.
So thank you very much. We don't have time anymore. No, one last question.
It's all right. Do you see any way to make this anode type actually type safer? Because
I spent a lot of hours on that. I'm not sure. Maybe not in Haskell. It's
okay.
So it is a somewhat intentional trade-off, since you don't have absolute type safety. Like I did have a version of this where you was annotating exactly what kind of tokens you would have. So like, for example, a let and then an equality sign and then there's a placeholder and stuff like that. I experimented with that, but it's not really convenient. So, and when you're designing DSL, it might also be quite nice to have like two different syntax forms that compile to the same AST node. And the moment you try to do that type safely, it gets very annoying, at least in Haskell.
The number of holes can actually be dynamic.
Exactly. So what we have in this example, terrible for that. Yeah. Okay. So here, the parameters. We don't have only two parameters. We might have an infinite, we might have an arbitrary amount of parameters because this is a list. So we can't really statically know the amount of placeholders that we might need.